waves. Okay, today that is theoretical expression. Today we will discuss about experimental procedure, how they confirm the existence of matter waves and how the matter waves.
Yes.
Hello,
Hello.
can you hear
Can
me
you hear
right?
me? Yes, sir. Yes, sir.
Yes, sir.
Okay, thank you. So, and the things we will discuss experimental evidence and properties of or characteristics of this de Broglie waves we will discuss. Okay. Now first just quickly go through that derivation part, how we solved the matter waves. Okay, what is the de Broglie hypothesis means? So every moving microparticle is associated with a wave. Okay, these waves we are calling a matter waves or de Broglie waves. So here generally wave is associated with a material particle or material particle, that is the de Broglie wave or matter waves. Okay, this is simple definition. So the main thing, the the particle should have some mass, and this is the microscopic level or atomic level, and it should have some velocity. So every material particle associated with a wave, this wave we are calling a de Broglie wave or matter wave. For that we have used the first Planck's radiation law is equal to h nu, is equal to h nu. From there you can write is mu is equal to hc by lambda. Okay, someone is okay. This is one expression, and second one we know Einstein's formula, mass energy relation is equal to mc square. This is expression 2. Using expression 1 and 2, you can equal these two formulas because these both are expression for energy only, right? mc square. Here 1c and here c will be cancelled out. You can rewrite this expression, lambda is equal to h by mc. Okay, this is in case of light. Okay, what we want in material particle are de Broglie waves or matter wave. In that case, suppose if you have consider a material of material is having mass m, okay, and velocity v, okay, then this material particle, okay, you can write the expression or lambda, that is lambda means wavelength for a matter waves. Okay, matter waves h by m into v. Okay, here light we are considering light, so velocity of light is c. Here we are considering material particle, velocity is v. Okay, this is you can write h by p also. Okay, this is the expression for wavelength of the matter waves. Okay, this is very simple expression, but this is very important question. Okay, we have derived in three special cases. One is in terms of kinetic energy. In terms of kinetic energy, case one. Okay, kinetic energy we know k kinetic energy is equal of mv square, right? Mv square. So from this expression we have derived mv is equal to 2m into ke, right? 2m into ke, that is under square. Just you substitute here h by 2m into ke, 2m into ke. This is kinetic energy. If you know kinetic energy of any material particle, you can estimate the de Broglie wavelength or wavelength of matter waves. Okay, second case, in terms of if you have any charged particles, charge is q and potential is v. So here kinetic energy of mv square is equal to q into v. Okay, we have seen this expression in photoelectric effect also. Suppose once in incident the light, electrons are ejected from metal, so these electrons get the kinetic energy from potential energy. We are giving some potential energy, these electrons getting some kinetic energy, are acquiring some kinetic energy, and that is equal to q into v. Okay, here also you can write lambda is equal, just you write lambda is equal 2m into q into v. V means here not velocity, it is a potential. Okay, potential in terms of volts or electron volts, whatever you can say. Okay, this expression if you take for electrons, if you take for electrons, lambda is equal to 12.26 by root v. Okay, root v, it is angstroms. Okay, lambda is angstroms. Okay, okay, this is the expression for electrons. Okay, so just you know electron mass and charge and h also, you know, just you substitute the values and you will get the lambda. Okay, that is the in terms of charged particles. Okay, second thing, third one is in terms of temperature. If you know in terms of temperature, suppose if you have any Yes, any doubt? Or are you asking any doubt, please?
Yes, sir. Second one, once you repeat again, sir.
Yeah, okay. I will repeat. Okay. So suppose if you have any particle, suppose if you take any particle here, we have any particle. Suppose we are giving some temperature, right? If you give some temperature, this particle will get some kinetic energy, right? This sorry, this is second
Yes.
one, right? Wait, just so second one you asked me, right? So see, when we discussed photoelectric effect, we have used some light here, some light or any photons. Okay, we incidents are some metal plates. Here electrons are ejected right from the metal plate. That is the photoelectric effect. So here we have taken two plates, two metal plates or any plates. So here we have applied some potential here. Okay, this is some potential here. Suppose because we applied a negative potential, this plate will get negative potential and this plate will acquire positive potential. So these electrons, how we are getting accelerated, we are giving some potential energy, we are giving some positive energy. That's why these electrons also having negative energy. These electrons attracted towards the positive potential. So here whatever electrons getting kinetic energy, that is half mv square. Generally we know kinetic energy is half mv square. That is how we are getting by applying some potential, that is equal to q into v. Okay, from this expression you can rewrite mv is equal, you can rewrite from this expression. Okay, mv is equal, just I am sending
Who is charge here, sir?
yes, sorry.
Who is charge here, sir?
Q is charge of that electron. Okay. Charge, electron charge. Okay. Electron charge, and I'm just writing Q M into QV. Okay. This V is the potential under square. Okay. Just you substitute this value in the wavelength. Then you will get this expression. This expression you will get lambda is equal to H by 2m QV. So our for electron, if you take electron, okay, we know electron mass 9.1 into 10 power minus 31 kg, and H we know, H value also we know, Planck constant. Okay, after that electron charge also we know 1.6 into 10 power minus 19 coulombs, and this one 6.62 into 10 power minus 34 joule second. Okay, so this value if you substitute, you will get the, we don't know potential, how much potential we are applying. So lambda is equal to 12.26 by root v. V is the potential. Suppose if you know potential of any electron, you can also estimate the wavelength of matter waves or wavelength of material particle. Okay, is this clear now?
Yes, sir.
Okay, just third one. Okay, if you take any particle, okay, if you give some temperature here, this material, this particle will move some different location. Okay, first here it is here, after some time it is here. Okay, so how this particle is getting kinetic energy, thermal kinetic energy, by giving some temperature. Here the kinetic energy is equal to, okay, 3 by 2 into kBT. This is a uh, 3 by kinetic energy equal to 3 by 2 K into T. Okay, here half mv square is equal, half mv square is equal 3 by 2 into K into T. KB or K you can write whatever, it's not a problem. Okay, this 2 will cancel out. Mv square is equal 3 kt, right? From this expression we want mv, right? So I am writing m square v square is equal, here I am multiplying m both side. Okay, 3m kt. Okay, 3m kt. From then we can write mv is equal to under root 3m kt. Okay, under root 3m kt. Now you can substitute in the lambda h by here 3m kb into t. T is the temperature, Kb is the Boltzmann constant. This value also you know. Okay, if you know temperature, you can also estimate the wavelength of the matter waves. Okay, this is three special cases. If they ask, derive the de Broglie wavelength, and if it is short answer, you write up to this lambda is equal to h by p. If they ask long answer, you have to derive these three special cases also. Okay, is it clear, everyone?
Yes, sir.
Okay, now this is the about matter waves. Okay, matter waves, just like it is also light, we know it is also sometimes behaves as a particle and sometimes a wave nature. Okay, it material particle also, material waves. Matter waves means, matter means just a particle or anything, any particle or material, it should have some mass. Okay, and if it is when it is moves, it behaves as a wave. Okay, it is associated with a wave. Any microscopic material particle or microparticle is associated with a wave. These waves we are calling matter waves or de Broglie waves. Okay, this is like similar to light waves. Okay, but here light doesn't have mass, but this material particle always have some mass. Okay, so here we will see characteristics of material particles. Okay, characteristics. What are the characteristics means what? Characteristics of matter waves. Matter waves. Okay, what does mean by characteristics? Anyone? What is the meaning of characteristics?
Functions.
Functions. And any other
Proper.
Natures.
properties, features. Okay, main features are main properties that will define our problem or anything. Okay, that will, suppose if you have, if you know device, any device, how you will see if you have transistor, suppose transistor. Okay, how you will see, suppose if you have a laptop, what you will see, you will see RAM and memory and speed, clock speed, this all you will see, right? These are the main features. Here also, to distinguish or to describe the any object or anything, you will study the characteristics. Okay, what are the main properties? Here also we will see this one. Okay, these are lambda is equal to, what is the first one? Lambda is equal to h by mv. Okay, first thing is this, for matter waves, first one is material particle always should have some mass. Okay, and velocity, these are the main point. Okay, otherwise if it is mass is 0 or velocity is 0, what is the wavelength here? Lambda becomes infinity, right?
Okay.
So this is not possible. So to existence of matter waves, this material particle always should have mass and velocity. Otherwise, we cannot say this is a matter wave. So means every material particle, it should in be, it is in be motion. It will be in motion. Then only it will have some velocity. Okay. Suppose it is in rest. Suppose material particle having mass, but it is at rest. So velocity is 0. In this case also we cannot say it is a matter wave. So always material particle should have velocity. Then only we can say this is a matter wave. Second one, lambda is always proportional to the, inversely proportional to the m, and also inversely proportional to the v. So suppose mass is small, lambda is high. Here also velocity is small, lambda is high, wavelength is high. Suppose if you take electron mass is very less. Okay, suppose we'll see some example here. Okay, electron mass is in terms of 10 power minus 31 kg, right? Suppose if you have cricket ball, the mass of cricket ball is like 100 grams. Suppose 100 grams. Okay, suppose if you calculate the wavelength, if you calculate the wavelength, the electron wavelength is very high compared to this cricket ball because mass is high. Okay, similarly this same thing also, velocity is less, so lambda is high. Okay, this is the second property. Third one, these are the not electromagnetic waves. These are not EM waves or electromagnetic, whatever you can say. Matter waves are not electromagnetic waves because, so electromagnetic waves means if you have any conductor here, if you have a conductor, if you electrons flowing in a conductor, because of this electron there is electric field, because of this electric field there is a magnetic field, right? But here we are not producing any electric field and magnetic field. Okay, that is the fourth one. Okay, fourth one, and this velocity of matter waves always greater than the light velocity, always greater than the light velocity. Now we will see. Okay, now we will see how this matter waves velocity is higher than the light velocity. Okay, now we know E is equal to mc square, right? E is equal to mc square, and we know we know uh, wave velocity is equal to, general wave velocity is called nu into lambda. Okay, here E is equal to, also we know h nu, right? H nu. From this expression, this expression and this expression, you can write h nu is equal to mc square. Okay, here nu is equal to what we can write? Mc square by h. Okay, just you substitute this new value here. Okay, so here nu is equal to mc square by h, mc square by h, and lambda is equal to h by mv. This is the lambda is the de Broglie wavelength. Suppose if you take any de Broglie wavelength matter wave, we are what we are calculating here, velocity of matter wave. Okay, velocity of matter waves or de Broglie waves, whatever you can say. Okay, matter waves. So here C is there. H cancel out. This H, and this M and this M will cancel out. What we will get? Velocity of matter wave equal to C square by V. C square by V. Okay, this is always, this value C square by E is always greater than the C value, right? Always greater than the C value. That's why this always material particle or matter waves velocity is higher than the light velocity. Okay, is this clear now, everyone?
Yes, sir.
So this is according to theoretically, but according to theoretically only. Okay, but we don't know experimentally light velocity is the highest value, right? What do you know? Highest value of velocity. What do you know experimentally? Have you got just after this class? What is the highest velocity? You type it. Okay, just you type it. Okay, this light velocity only what we know is highest velocity, but theoretically this is material particle is having higher velocity compared to light, but this is theoretical only, experimentally not proved. Okay, is this clear? Okay, these are the some properties. Okay, just you note down these properties. Okay, studying these properties you can say this is this matter wave or some other wave. Okay, these are the some characteristics. Okay, now we will see the up to now, is this clear? Up to now this class is clear.
Yes, sir.
Okay, now we'll go to the second very important one, division German experiment.